Well, hey there, this is Mrs. Sharp, and I'm going to go over some 2.3 notes with you. And here we go. Here is the learning target that's right in your notes. This is what we're going to go over quickly. You did this in groups, took notes together. I just thought maybe this would help sort of reinforce what you talked about in your groups, make you feel a little bit better if you have been feeling iffy on these things. So here we go. Let's talk about properties first, and we're going right in order through your notes here. Properties are the set of characteristics that we can use to describe something, and we can also use to recognize something. Two types of properties: physical. Physical properties are determined by appearance or through the senses, and they do not change the substance in any way. And physical properties can be broken into two categories. We have extensive physical properties, and these depend on how much of a sample of the material we have. So that means, since it depends on size, we can't really use it for identification. Here's some examples. Mass, weight, volume, and length. There are other things too, but if all I know is that this particular substance has a mass of 5 grams, that really doesn't narrow down what that substance is for me at all. Just by knowing it's 5 grams, it can't tell me if I have silver or if I have salt or if I have water or what I have. It just is this extensive physical property. I think of extensive like if I extend the size, then the property would change. If I extend the size, the property would change. That's how we know it's extensive. Then we have these intensive physical properties, which can be used for identification because they're the same no matter what the size of the sample is. So there's lots of examples of these. We have color. We have odor, like if it's volatile. Volatile means a gas forms easily. We have if it's taste, which we would never directly do. We have its state, solid, liquid, or gas at room temperature. We have its hardness or texture. If it's malleable or not. Malleable means I can flatten it with a hammer. If it's not malleable, I can't flatten it with a hammer. Its density, which does not depend on size. Its solubility, whether or not it dissolves in something else. Its conductivity, so if it conducts heat or electricity through it. Its melting point and boiling point. If it's ductile, if it can be pulled into a wire. Oops, let's go back. These are all things that do not depend on the size of the sample at all. So no matter how much I have, a little bit or a lot, its color, if it's always gray, is intensive. If it's always a liquid at room temperature, then that is an intensive physical property. It doesn't matter if I have a drop of it or if I have a bucket of it. If it conducts electricity, it's going to do that no matter if it's a big sample or a small sample. If it's a big sample or a small sample, its melting point and boiling point is going to be the same. So these things do not depend on the size of the sample. But remember, extensive, if I extend the size, that's going to change the property. So these are all physical properties, meaning they don't change the identity of the substance. Chemical properties do change the substance because it's a behavior with a reaction. It's a chemical change. So it undergoes a chemical reaction and it forms a new substance. That substance has different properties. That could be the ability to burn, which is called combustion. It could be the effect of heat, light, and electricity, but the main point is that when I'm done with testing that chemical property, it's no longer going to be the same substance. So I don't know if you guys remember the whoosh bottle that I did for you towards the beginning of the year, but one of the chemical properties of isopropyl alcohol was that it is combustible. And when I was done, if I were to try the whoosh bottle again, it would not work. And that's just because what's left over in the whoosh bottle is completely different and has new properties. It's not combustible anymore. Its ability to combine with other substances like air or water or gas or any other substance is also a chemical property which would change the substance. When it's with oxygen, we call it corrosion. You can think of like as rusting. Let's talk about how physical and chemical changes are different. Any change in matter involves energy changes. We've talked about this before. Now, nuclear would have the most energy change, and then chemical, and then physical would have the least amount of energy change, but they all have some. And in every single change in matter, energy can either be absorbed or released, and we've talked about these two terms quite a bit. A physical change is one that doesn't destroy the identifying properties of the substance. In other words, we don't change what the substance actually is. No new substances are formed. The properties can be restored. It could be a change in phase. And this should say C 2.1, not 1.2. I was having a dyslexic moment there. Change in form, grinding, dissolving, mixing. These are all changes that don't change what the substance is, it just changes kind of the form of the substance. So for example, if I were to take water and boil it, if I boil water, it goes from water liquid to water gas, but it's still water. It's still two hydrogens and an oxygen stuck together. That's why it's a physical change. A chemical change is any change in a substance that does destroy the identifying properties of the substance. So we do make something new. It's a chemical change with something new made. New properties result. We always have reactants make products, and that's usually irreversible. And then these are our 7 indicators of chemical change. You should already have these written down. They might be in a different order. But these help us know that a chemical change has occurred. So if I see one of these 7 things happen, or multiple 7 things happen, then I will know that this is a chemical change. Okay, so here we go again. Color change, odor change. If I make a gas where I didn't have one before. Careful with this one. We can't just go from a liquid to a gas. That's a phase change. It just means actually making a new gas where I didn't have a gas before. A precipitate formed when 2 liquids are combined. A solid is formed. It kind of looks cloudy. We've seen a precipitate before. Heat evolved, so you might feel some heat released. Or heat absorbed, you might feel some coldness. And if you see light, like flame or sparks or glowing, like a glow stick, all indicators of a chemical change. And you often have many of these happening at the same time. So before you decide if it's a physical change, ask if it's a change in phase or a change of form. If it's a chemical change, look at for one of those reasons from the list. So you can say a gas was produced and heat was released, then there's a good chance that it's going to be a chemical change. So we need some evidence for that. Moving on to the law of conservation of mass. The statement of the law is this: mass matter is not created or destroyed during physical and chemical reactions. The quantity of matter remains unchanged. Now, physical and chemical, notice that it does not apply, and it says this again down here, to nuclear changes. So we are talking about the law of conservation of mass only for physical and chemical changes. So the mass that I start with should be exactly equal to the mass that I finish with in a physical or chemical change. So whatever reactants I start with, if I were to take the total mass of that system, then that better be the same as the total mass of my system at the end. So this is an example problem, and it's in your notes. It says kidney stones are made in the following chemical reactions. So you can see that right here are your reactants, and you're using 50 grams of each. That means my total mass is 100.0 grams. Then it's saying over here you have 33.7 grams of just this hydrogen carbonate. Then it's asking how much calcium oxalate was made. Well, whatever it is, it better add up to equal 100, because the total mass of your reactants has to equal the total mass of your products. So if I subtract 100 minus 33.7, I get 66.3 grams. So I'm going to have 66.3 grams of calcium oxalate. And that would add up to 100. Here's another one. Magnesium is burned in the presence of oxygen to form magnesium oxide in the following reaction. It says if 6 grams of magnesium was used and 10 grams of magnesium oxide was made, how much oxygen was required for the reaction to occur? So I've got 6 grams of magnesium. I don't know how much oxygen I used, so I'll put an X. And 10.0 grams of magnesium oxide was made. So one thing that I wanted to point out with this is that the equation is written a little bit differently this time. We have formulas as opposed to words. And we have like this big 2 here and this 2 here. Those numbers don't affect the overall mass. So those have nothing to do with the masses down here. So we can basically ignore them completely. I still need the mass of my reactants to equal the mass of my products. So 6.00 plus X, 6.00 grams plus X equals 10.0 grams. If I subtract 10.0 minus 6.00, I should have just one decimal place, least number. And that means my oxygen is going to be 4.0 grams. Because if I add those two up, I'm going to get 10.0. So I hope that that maybe helped reinforce some ideas you've been talking about in your groups, help you feel a little bit better about some physical and chemical properties, changes, and law of conservation of mass. There you go. Have a great day.